Okay, I hope I'm audible to all students who are attending this particular lecture for Advanced Econometrics course. In this particular lecture, I continue with the discussion of regression analysis with time series data. If all students can recall that in my previous lectures on time series analysis, we have looked at some important terminologies and the difference between the cross-sectional and the time series data. We have also looked at some important models in time series analysis. We have looked at the static model, which is one of the simplest models for time series. After that, we have also looked at finite distributed lag models, and we have also done autoregressive distributed lag models in the previous lectures. In my immediate previous lecture, if all students can recall, we had also done a practice problem based on time series analysis. Okay, so now in this particular lecture, we are going to look at some important properties of OLS under time series analysis. Remember, when we were doing the cross-sectional analysis, we had done some properties of OLS, some assumptions of OLS when we were doing cross-sectional data. Now, in this particular lecture, we are going to look at the assumptions of OLS under the time series analysis. Okay, so let's quickly start with this particular lecture. I'm just writing the main heading for completeness. We are looking at regression analysis with time series data. We continue with our lectures on this particular module. Okay, the books I prefer to follow as reference for my lectures on this particular module. This is Econometrics by Woolridge. And along with this, I also prefer to follow Basic Econometrics by Gujarati and okay. So let's quickly look at the finite sample properties of OLS. So students can write the heading, finite sample properties. Finite sample properties of OLS under the classical assumptions. Based on time series data. Based on the time series data. Okay, so let's look at time series assumption 1. So before that, I can write that, so I can write assumption TS1. Assumption time series 1. I'm exactly following the Woolridge book for this particular topic. Okay, so I can say that the stochastic process, where I have a set consisting of the explanatory variables xt1, xt2, xtk. So I have k independent regressors at the time period t, and I have yt, and t itself is a time period which goes from 1 to n. So basically xt1 is the regressor, is the first regressor, okay, taking the value at time period t. xt2 is the second regressor taking the value xt2 at the time period t, and so on. So there are n time periods, and there are capital K regressors. So this is the stochastic process. This follows the linear model. The first assumption is telling us that it follows a linear model. That is, yt is equal to beta naught plus beta 1 xt1 plus beta 2 xt2 plus dot dot dot. I can stretch it to beta k xtk plus ut, where
UT is a population disturbance term at the time period t as t takes values from 1 to n. So UT I can say is the sequence of errors or disturbances. It denotes the sequence of errors or disturbances. And n denotes the number of observations, or I can say in a better way, number of time periods. N denotes the number of time periods. Okay, so the first assumption in time series analysis is telling us that the stochastic process consisting of k regressors and yt at time period t as p varies from 1 to n is going to be a linear model. When I say linear model, it's linear in the parameters. The parameters are beta naught, beta 1, beta 2, dot, 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 beta 3. Remember, a linear model means a model linear in the parameters. So it's a linear model, okay, where UT denotes the sequence of errors or disturbances and N denotes the number of time periods. Okay, so I'm just writing a note to make it more clear. So I can say that in the notation xtj, t denotes the time period, t denotes the time period, and j denotes one of the k explanatory variables. One of the k explanatory variables. The point to understand here is that I have k independent variables across n time periods. So I can say therefore there are k independent regressors. There are k independent regressors across n time periods. Each regressor takes values across n time periods. So students should not get confused with the notation. There are k x's. Each of these x's are taking values over n time periods as t goes on from 1 to n. Okay, so I hope students have understood this and have no doubts. I can also, denote it like a vector. So I can erase the initial part and I can write, if I erase this initial part off, erasing this part off, I can write on the top that let xt be a vector which takes which is nothing but xt1, xt2, dot 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 xt2. So I can call it as a vector. So I can darken it. This is actually a vector. It's a vector at time period t, which goes from xt1, xt2 to xt2. It denotes what? It denotes the set of all the independent variables. It denotes the set of all the independent variables in the equation at time t. In the equation at time. Okay, and if I talk about capital X is a vector which itself consists of the vector in time period 1, the vector in time period 2, dot 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 the vector in time period t. Okay, and t goes from 1 to n, so the vector in time period. Okay, x1 is the vector in time period 1, which is xt1, x2. I can write where x1 itself is what? Where x1 itself is x x11 x12 dot x1k. Remember, xt is x. I can write, if I write xt is xt1 xt2 dot xtk. So x1 is the vector at time period 1. That's x11 x12 x1k, set of all possible regressors in time period 1. X2 is the vector in time period 2, which consists of set of all possible regressors at time period 2, which is x21 x22 dot x2k. And dot xn is the vector in time period n, which takes values xn1 xn2 dot xn. So students in the advanced econometrics course should also start getting comfortable with the vector notations. xt is the vector at time period t, which consists of set of all possible regressors from 1 to k, at time period t. x1 is the vector in time period 1, which consists of set of all possible regressors from 1 to k in time period 1. x2 is the set of all possible regressors in time period 2. So from 1 to k, regressors from 1 to k in time period 2, and so on. And capital X denotes the set of all possible vectors across different time periods, where x1 is the vector for time period 1, x2 is the vector for time period 2, and I have n such time periods. So xn is the vector in time period n. Okay, so the first assumption I'm summing up, it's telling us that for the stochastic process involving time series data, the regression model is a linear model. Linear model means that is, I can say, linear in parameters. I can write here linear in the parameters, that is the betas. Therefore, this is how my regression model looks like for time series data. We assume a linear model, linear in the parameters. Okay, erasing all this off, let's look at assumption TS2, assumption time series 2. Assumption time series 2. This assumption is again talking about no perfect collinearity. Although we would expect some degree of collinearity, but it's not perfect among the explanatory variables. So I can write that in the sample, and therefore in the underlying, in the sample and therefore in the underlying time series process, no independent variable is constant, nor a perfect linear combination of the others. Nor a perfect linear combination of the others. So the second time series assumption is telling us that when we talk about the time series process, the independent variables are no longer constants. They are going to change with time. They are not going to take constant values with time. They are going to change with time. And one of the independent variables cannot be expressed as a perfect linear combination of others. From the mathematical economics course, we all know how to write a linear combination of two variables. So what I'm trying to say is that one of the independent variables in the model is not a perfect linear combination of other explanatory or independent variables in the model. So I can further write a note. I can write a note that assumption TS2, assumption time series 2, does allow the explanatory variables, to be correlated, but it rules out perfect correlation in the sample. It rules out perfect correlation in the sample. That means the independent variables in the sample should not be perfectly correlated with each other. That is what assumption TS2 is telling us. Then let's look at assumption TS3. The students can now write the heading assumption time series. The third assumption for time series for OLS. This is based on the TS2 was no perfect collinearity. TS3 is zero conditional mean. This is a very important assumption. Zero conditional mean. So let me explain this. For each time period T, the expected value of the error ut, the expected value of the error ut given the explanatory variables, and here comes a very important phrase, for all time periods. Given the explanatory variables for all time periods is 0. That means the expected value of ut conditional on explanatory variable, not just for one time period, but for all time periods, be it the past, be it the present, be it the future. Expected value of ut conditional on explanatory variables in the past, present, future is equal to 0. So I can write mathematically expected value of ut conditional on the vector capital X, where the vector capital X denotes the set of all vectors across all time periods, where time periods go from 1 to n. Remember, a few minutes back, I wrote vector capital X. Vector capital X is x1, x2, dot, 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 xn, where all of these themselves are vectors containing k independent regressors. The expected value of ut conditional on x is equal to 0 for t taking values from 1 to 2n. So I can now write a note further to explain this. Assumption TS3 implies that the error at time t, that is ut, is uncorrelated with each explanatory variable. It is uncorrelated. The error ut is uncorrelated with each explanatory variable in every time period. Each explanatory variable in every time period. Okay, so hoping that students have understood this particular assumption. What I'm trying to say is that the conditional mean value of the error term ut across x's in all time periods is equal to 0. Okay, so if I quickly move forward now, so I can further elaborate more on this. If I compare this with the time series data, if I compare this with the cross-sectional data, in the cross-sectional data, ut was mean independent of only xt. Here, ut is mean independent of x's across all time periods. That is the main difference. So if I erase the initial part of, I am erasing assumption TS2. I'm erasing the initial part of. So what I wrote at the bottom of the screen, I can call it as within the notes. This was point number 1. Within the notes, this was point number 1. Point number 2 on the top. Given the cross-sectional data, Given the cross, I can write, given the cross-sectional analysis, given the cross-sectional analysis, it is not surprising that we require UT to be uncorrelated. We require UT to be uncorrelated with the explanatory variables, at time t. That is, according to the cross-sectional data, expected value of UT conditional on the regressors only in the time period t, which is xt1, xt2, xtk, which I can call as expected value of UT conditional on, guys, this I can call as my vector xt. This is my vector xt is equal to 0. For the if I compare the time series with cross-sectional data, what am I aiming at? I am trying to convince all students that in the cross-sectional data, the population error term UT is only mean independent of XTs. But in the time series analysis, my error term UT is not only mean independent of XTs, it is mean independent of all X's across all time periods. That means the population error in UT is not correlated with all the X's in the past also, in the present also, in the future also. UT is not correlated with the X's in the past, present, and future. That is what time series is telling us. So I can write, if I call this as, let's say, equation star, I can say that when equation star holds true, when equation star holds, we say that xpj are contemporaneously, another easier word is instantaneously, exogenous. That is, equation star implies that UT and the explanatory variables, are contemporaneously or instantaneously at one particular point of time, not over a period of time. At one particular point of time, are contemporaneously uncorrelated. They are contemporaneously uncorrelated. That is, the correlation between xpj and ut is equal to 0 for all j. That means the population error term ut is uncorrelated with xtj as j takes values from 1 to k. Another way of saying it is this equation only. What I'm trying to say is that in cross-sectional analysis, UT is uncorrelated with all the independent variables at time t only. But if I talk about assumption TS3, the only thing is, guys, I'm explaining it in more depth. Otherwise, those who would have understood it by now. Things are getting a bit repetitive because I'm trying to, pay more weightage to the explanation part. But if you've understood it by now, I think then that's fine by mine. What I'm trying to say is assumption TS3, I can write further. Assumption TS3 requires more than contemporaneously exogenous, more than contemporaneous exogenity. That is, UT, according to the time series assumption, UT must be uncorrelated not only with xtj as j takes values from 1 to k, but ut must be uncorrelated with, it must be uncorrelated with all the explanatory variables, that is x's across all time periods t going from 1 to n. Okay, I can further write here, it should be uncorrelated with all the explanatory variables xj's as j goes from 1 to k across all time periods as t goes from 1 to n. So this whole paragraph is telling you the difference between the assumption made in the cross-sectional analysis and the assumption made in the time series analysis. The cross-sectional analysis assumption is more instantaneous or contemporaneous, in which ut is only uncorrelated with the xt's, xt1, xt2, xtk, because there are k such independent variables. However, the time series analysis says that ut is not only uncorrelated with the xt's, it is also uncorrelated with the past and the future values of x's also. Okay, and then I can write the third point of the note, for which I erase this particular part of. Let's write the third point of the note. The third point is telling us it is important to understand, it is important to understand that the assumption TS3, the assumption TS3 puts no restriction, it puts no restriction on correlation in the independent variables, in the independent variables, or in the ut across time. That means the independent variables can be correlated over time. There should not be a linear combination of each other. There should be no multicollinearity, but the independent variables can be correlated over time. That means x1, the independent variable x1 can be correlated over time. That means so I can say that is x t minus 1 1 and x t1 can be correlated. What is xt minus 1 1? It's the value taken by the independent variable x1 at time period t minus 1, and xt1 is the value taken by the independent variable x1 at time period t. These can be correlated. Similarly, in the bracket I can write, similarly ut minus 1 and ut can be correlated. There is no restriction put by TS3 on these. So assumption TS3 relaxes the assumption. It puts no restriction on the correlation in either the independent variables, which are the xi's, or the error term ui's over time. They can be correlated over time. So I hope all students attending this lecture have understood assumptions TS1, TS2, and TS3 and have no doubts. I can now write a theorem. If I erase all this off, I can now write a theorem which gives me the unbiased property of the OLS, unbiasedness of the OLS. I can write that if the assumptions, if the assumptions TS1, TS2, and TS3 hold true, the OLS estimators, we have done OLS procedure in our simple linear regression model, ordinary least square procedure. The OLS estimators are unbiased, conditional on the vector capital X, where capital X includes all possible explanatory variables across all possible time periods. And therefore, the OLS estimators are unbiased unconditionally as well. They are unbiased unconditionally as well. Unconditionally means not conditioned on any X. That is, mathematically, I can write expected value of beta j hat is equal to beta j as j takes values from 1 to 50. This is a very important result, what we have learned today. If the time series assumptions 1, 2, and 3 hold true, all the beta j's are going to be unbiased both conditionally on X or unconditionally. That means we all know the definition of unbiased. We all know the unbiased property, expected value of beta j hat, which I get from the sample, is equal to the population beta j, as j takes values from 1 to 4. Okay, so I stop now in this particular lecture. The objective of this lecture was to discuss with all students time series properties 1, 2, and 3, and look at a very important theorem which comes from assumptions TS1, TS2, and TS3 holding true. In the next lecture of time series analysis, I am going to start the discussion with assumption TS4. We are going to start from the discussion of the fourth assumption in time series analysis in the next lecture. I stop in this lecture. I hope students have enjoyed this lecture. Any doubts, you can unmute your mic and ask, or you can get in touch with me for doubts on call or WhatsApp, or you can mail me your doubts at divineschoolofeconomics@gmail.com. This is where I stop in this lecture.